Yeah. I'm not the Messiah. Okay, so like I said, I'm going to talk mostly about just basics of Gaussian free field. So, is that funny? Okay, so I guess let's just do like 5 minutes, like I said, of what is Gaussian free field. Okay, so and personally, I like what Wendelin said, that it's kind of different things to different people. And I actually like Wendelin's approach best, that you have some domain D, right? And I'm going to talk about zero boundary GFF. Okay. So, you know, I like to think of it just as a function from the domain into the reals, and it's a random Gaussian function. And since it's Gaussian, all you have to do is specify its mean and its covariance structure, right? So the mean of this thing is just, well, you just assume it has mean 0. Might as well. And that matches up with the boundary conditions. And the covariance structure is just given by the two-dimensional Green's function, right? So this is the Green's function for this domain with 0 boundary conditions. Okay? Now, the problem, of course, is that this thing blows up when x equals y, right? So that says that the variance of h of x would be infinity. So that's why this thing cannot be a random function, right? You cannot realize this Gaussian free field as an actual random function. But the dirty little secret is that whenever you're doing computations and stuff, you just pretend that it is, right? You always just pretend that it's a random function with this covariance structure. And then afterwards, you come along and you clean it up, right? So we'll try and do that, I guess. But let me briefly mention the Gaussian Hilbert space approach. So okay. So this is a little bit more formal. So a Gaussian Hilbert space as well, basically it's just, you start with some Hilbert space, your favorite Hilbert space, like L2 or, I don't know, whatever, even just Rn if you want. And what you do is, what makes it a Gaussian Hilbert space is to each element of the Hilbert space, you associate a normal random variable. Okay? And then you have this big collection of normal random variables that are indexed by the elements of the Hilbert space. And the covariance structure of the Gaussian random variables is given by the inner product of the Hilbert space. Okay? So you have, let's say, just for every, I should briefly say it like this. For each f and h, you have some random variable, which is quite often written like h inner product f, right? And so this is some normal random variable. Let's just say mean 0. And the variance of it is just f with itself. Okay? That specifies the variance. You really need the covariance structure to fully understand a big collection of Gaussians, right? So if you have two things, if you have two elements h sub f and h sub g, well, then their covariance, just by definition, is given by the inner product of those two things. Okay? That's just by definition. So for the Gaussian free field, what you do is you just take a particular choice of the Hilbert space, right? So you look at, well, and again with 0 boundary conditions, we'll stick to for now. So you look at the space of all functions on D, all smooth, compactly supported functions on your domain. And then you take the Hilbert space closure of that, where the norm in this case is given by this Dirichlet inner product. Okay? So we're always going to use this Dirichlet inner product. Fg inner product is the integral over D of grad f dot grad g. Okay? So that's the inner product we use throughout. And then you let Hs of D, that's the Hilbert space closure, of smooth, compactly supported functions in D. Okay. So this is your big Hilbert space, and all you're doing is you're saying for each element in this space, you're identifying with it a normal random variable. And this is the covariance structure between different elements of the Hilbert space, or between different random variables. Right. This one here. This I was just trying to be general here. This is for like a general Hilbert space, and it's whatever the inner product is for the Hilbert space. But no, I'm just saying this is just a notation. It's the usual notation for this is the normal random variable associated with f. You think of it because, you think about f, h is actually acting on, h is an element of the Hilbert space, and so it's acting on, yep. No, here, but this is complete generality. I'm not saying what the Hilbert space norm is here or anything. I'm just saying for a general Hilbert space, this is what you do, right? Yes. H, F is just notation. Yes, exactly. No, it's not the actual inner product. It's just notation. That's how I like to think of it. I mean, it's not. I mean, sometimes you can realize it as an actual inner product, right? In this case. But most of the time, I like to think of it as just notation. So that's purely symbolic notation for this random element of just a normal random variable. That's all it is, right? This is a normal random variable with mean 0 in this covariance function, or this variance. Sorry. Okay. So in this case, so for every f in this Hilbert space, you write hf inner product, and usually at least Scott puts the little gradient symbol here. Okay? Now again, this is still purely notation. This just means the element or the normal random variable associated to this function f. Okay, so it's a normal random variable It's a normal random variable associated to f. Okay. And again, now so its variance will be just the Dirichlet inner product of f, and the covariance will just be f inner product g with this Dirichlet norm, right? This Dirichlet inner product. Now, okay, so I didn't mention, it's not quite clear at this point that you can actually do this. You take some arbitrary Hilbert space, and then for every element in that, you can associate a corresponding normal random variable such that they have this covariance structure, right? It's not immediately clear you can do that, but it just follows from it's abstract nonsense is what it follows from, right? The best place to look on this if you want to actually understand the abstract nonsense, which I don't think there's a lot of value there, but anyways, if you want to, there's this book, I like the book Gaussian Hilbert Spaces actually by Janssen. I don't know how to say it. Okay? Yep. What does the S mean in this HS? No, I think it's just for smooth, I think. Yeah, I don't think there's any, I think that's all the S means, yeah. It's the closure of smooth functions. Ron? Okay. So is this clear? You have this, to this thing you have associated this. Okay. Now, a lot of people have been sort of, okay, so you can't realize the Gaussian free field as a function, right? So instead you make it this, you can make it this type of thing, this type of Gaussian Hilbert space approach. All right? Now a lot of people ask questions about, so one of the central things Scott talks about is this circle averaging. right? So he has this, once you have h, then he talks about this h epsilon. So let me, so he talks about this h epsilon, which is supposed to be the average of the Gaussian free field on the circle, right? Now, okay, let's just spend a little time on what exactly that means, or how precisely you can define that. Okay? So I always do it like this way. I always describe what you want h to be, and then how you actually construct h, how you construct this h epsilon. Okay? So what you want it to be is you take the circle, you take the circle of radius epsilon, centered at z. So points w that are distance epsilon away. You integrate h on that. And of course, then you just divide by the circumference of the circle, right? So 1 over 2 pi epsilon. Okay. Now, another way to write this, purely formal, this is what you want. Everything at the first little while here is going to be purely formal, okay? Then we'll come back and we'll make a proper definition at the end. Another way to write this is, well, let's write it like this maybe first. So this is the integral over the whole domain of, say, h of w, integrated against the uniform measure. So this is just you're integrating h against the uniform measure on the small disk around z, right? That's all you're doing with this thing here. So let's write this as mu of z comma epsilon. Okay? So this is uniform probability measure. The circle, right? The circle. Okay, I always say that wrong, so that's a good thing to catch me on. So this is uniform measure on the boundary. Okay? No. So D is the whole domain, right? But all you're really integrating against is W on the actual circle itself, right? Now, if you want, you can write this is H inner product with this measure. This is purely formal again, right? But this is an L2 inner product, right? L2 of D of your domain. Okay. Now, the important formula, which I never wrote down, and I meant to, is that when you have this type of function, whoops, okay. I'm going to rectify this here first. Does this thing keep cutting out? No? Okay. So when you have this type of function, right? If you have say you have two smooth compactly supported functions, right? F and G, and if you ask what's F inner product G in this gradient norm, right? By definition, that's just integral of grad F dot grad G. Okay? But if everyone remembers, divergence theorem, I guess, or whatever, just integration by parts in multiple dimensions, this is the same as integral of F Laplacian G, except you pick up a negative. Right? So that's just integration by parts. And so this is the same as, that's just F negative Laplacian G, but in the L2 inner product. Right? Not the gradient inner product, right? So that's just integration by parts. So now what we can do is we can take that thing here. Here we have this h epsilon of z. It's h inner product with this uniform probability measure, right? But L2 inner product. But now using this identity, you can transform this back into a gradient inner product. Right? So you have to be careful. You already have, since this is L2, basically you have to think about the negative Laplacian is already in front. So to get back to the gradient thing, you have to do h. Well, you basically put Laplacian inverse on the other side, right? and that's the gradient inner product. Okay? Just straightforward application of integration by parts, right? But now, what is this thing right here? Right? That's what you wanted. You end up with this thing here just by some silly algebra. And you end up with, well, this right here, this is a well-defined element of the Gaussian Hilbert space, right? I mean, the only thing you have to check is that this thing here, the negative inverse Laplacian of this uniform probability measure, you just have to check that that's in your Hilbert space, right? It's in the closure of smooth, compactly supported functions. And I mean, you can check that it is. In fact, in a minute, we'll just write down what this thing is, what this inverse Laplacian of this thing is. Okay? Yeah. Which one? Little h? No, little h is not. So this is just, remember again, this is just the normal random variable that's associated to this function. That's all it is, this inverse Laplacian. Okay? So that's a way of defining the circle average, you see? Was it clear? Or is it more confusing? I don't know. Nicola? Yeah. No, so it's in the sense of, no, that's true. That's true. But in this case, I mean, the measure is so nice that you can, not only can you do it, you can write down exactly what Laplacian inverse is, right? And that's what we'll actually do. So what sense is it in? That's a good question. I don't know, I mean, this means, of course, just convolve with the Green's function, right? That's all it's going to mean. So we're just looking for, when we say this, we're saying, what is the function whose Laplacian is given by this, has this uniform probability measure, and has zero boundary conditions, right? With the Green's function, yes. Yes, it will give you an actual function. Yeah, will be this measure. Yeah, yeah. I mean, I'm not sure how strong you can make the sense in this case exactly. When you take the Laplacian of this thing, you'll get back the uniform probability measure, but it's probably in the sense of like generalized functions type thing. But maybe you can make it a little stronger even. I'm not sure in this case. Okay. Yeah. Yes, exactly. I mean, the inverse, if you change the boundary condition, the inverse Laplacian changes, right? Your Green's function changes.
But that's just the same as adding an harmonic constant.
Yes. Yes. So yeah, so if you use boundary conditions that aren't zero, if you put, your favorite boundary conditions on, but Dirichlet, when you specify the actual boundary data, then in the end, this thing is just equivalent to adding on the harmonic function that interpolates that boundary data. We can say that again in a minute if you want, but I think for now it's easy. It's easiest just to stick with zero boundary conditions for now. Okay. So you can take this as the definition of the circle averaging, right? For each z and epsilon, you have this element of the Gaussian Hilbert space. Okay? Now let me just briefly say. So this is a function. It's a function of epsilon and z, right? So you can ask, okay, I mean, what kind of object is this thing actually? As a function of epsilon and z. Right now, I just actually wrote that it's, I wrote it like a function. I mean, is it actually a function? H itself wasn't a function, right? So what about the h epsilon thing? And what you can do is you can actually check. You can check that that you can realize this h epsilon thing as an actual function from the domain into the real numbers. Okay? So it's an actual function. In fact, you can check that it has a certain amount of Holder continuity too in z. And in fact, it even has a certain amount of Holder continuity in epsilon. So in fact, this thing, you can check that this thing is, or at least that there's a version of this thing which is jointly Holder continuous in both epsilon and z, and that's jointly Holder continuous with any exponent strictly less than 1/2. Okay? That's just something you can check. I'm not going to go over that. And if you want, I'll... I think it can be improved actually, but I'm not sure. So if you look at Scott and Bertrand's paper, it says just 1/2 for both. But I think I don't know, I think it can be improved for Z, no? Yeah, in Z. In Z also?
Yeah.
Really? You can't make it better?
Well, I mean, no, you can't make it better.
Okay. Okay. Okay, let me get rid of this. Oops. Yeah. So let me just list this as a fact. You can check that if you use this, the standard Kolmogorov-Sentsov type theorem, it implies that there exists a version of h epsilon of Z as a function from, how am I going to write this? As a function from, say, epsilon Z in 0 infinity to cross D into R. There exists this function that is it's jointly Holder continuous in both variables. And that's for all eta less than 1/2. Yeah. And if you want a little proof of that fact, you can check in that in Duplantier Sheffield. But for now, it's nice to know that it's enough to know that for us this is just a function. Okay, it's a function of Z. Now I was going to say, what was I going to say? Oh right, I was going to mention what is the inverse Laplacian of this measure right there, right? What is the actual function corresponding to this uniform probability measure? So this is helpful. This helps you understand the covariance structure of h epsilon Z. Okay, so let's look about what is the inverse Laplacian of that probability measure. Okay. So it's easiest to figure out if you pretend that your domain was just the entire plane. Okay, so you begin with the domain is C. So then what you have is you have your point Z, and you have your ball of radius epsilon. And basically you're putting a uniform charge distribution on the circle, right? And you ask, what's the potential corresponding to that in the full plane? Okay. So let's, how am I going to write this? Let's write this first of all as, let's write it as G epsilon Z of W. Okay, so I want to write this this is the inverse Laplacian of this thing. So what will it be? Well, so if you're inside the circle, then the potential is constant, right? And this is the basic physics fact, that inside the circle, the potential is constant, right? All you have to do is figure out what the constant is. So let's not worry about that for now. Outside the circle, what's the potential? Well, okay, one way you can do it is you can say, this is my favorite way to do it, is just say, first of all, what's the Green's function in 2 dimensions? The 2D Green's function is just, so the Green's function for the entire plane, it's just negative log of x minus y. Right? Up to some factors of 2 pi that we'll just forget about. Right? So that's your Green's function in 2 dimensions. Now, if you're outside the circle, well, remember, it's Gauss's theorem or something, right? It's a consequence of the divergence theorem that having a uniform charge distribution on this circle is the same as if you just put a point amount of charge at z, right? Right at z. So this is exactly, the potential outside is exactly equivalent if all the mass was just concentrated at that point. And so that means the Green's function for this particular thing is given exactly by this when you're outside the circle. Okay? With the center point is z. Right? So so if you're outside the circle, the potential is just log of w minus z. Right? Yep. Yep. Exactly. So but I don't want to write down what the Green's function is per se for the domain. It's, well, you could, I suppose. This is equivalent to what I'm doing here. But, yeah. This is just another way of doing it. This is a way of doing it for this particular measure that you're trying to take the inverse Laplacian of. It's a little bit of a trick, but it's nice. It doesn't require a whole lot of computation. Just a little bit of believing or recalling your, the Green's function for the whole plane or for, yes. Yeah. Yeah. Up to 2 pi's again, but okay. And like I said, now in the center you're going to get a constant. The potential is constant, right? No matter where you are, you feel the same amount of force. Okay. So all you have to do is figure out what the constant is, but basically you just choose the constant so that this is continuous, right? So this is continuous across the boundary. And when w minus z equals epsilon, well, it's just log of epsilon, right? Or minus log of epsilon. All right? So that's the Green's function as if, again, this is only in the case where the domain was the whole plane, right? This doesn't work for the domain we're working in because the domain we're working on, we want 0 boundary conditions, right? So we have to somehow get 0 boundary conditions on this thing. Okay? So how do we do that? Well, maybe I didn't state it, but so let's put a C here on this thing to indicate that this is the Green's function for the whole plane. For the D thing, what we're trying to solve, remember we're trying to solve this equation basically to find the inverse Laplacian. We're trying to solve, we want the Laplacian of, so we want a function G, which depends on epsilon and z in the domain D, whose Laplacian with respect to W, we want it to be equal to this measure, this uniform measure. What the hell did I write that? Mu of z epsilon. Okay. Probably negative Laplacian. And we want the boundary conditions of this thing to be, we want this to be 0 for W on the boundary. That's what we're trying to solve for. Now we already have this guy for when D is the complex plane. So how do we do it when D is just some subdomain? Well, basically what you do is you try and find a harmonic function So let's see. So the problem with this guy is it has the wrong boundary values, right? On D. So what are the boundary values of this guy on D? So this is negative log of, well, w minus z for w in the boundary. Right? That's just by definition. I mean, so what I'm assuming also, I'm silently assuming that, that whatever my domain D is, that epsilon is small enough so that this ball is strictly inside. Okay? Let's assume that too. It just makes life easier. All right? So this has the wrong boundary conditions, but it does satisfy, but this already satisfies this part, right? We know that. That's how we constructed this, this GC such that its Laplacian is exactly equal to this uniform probability measure. Okay? So it satisfies this part, but not this part. So we can correct for this part, right, if we subtract off a harmonic function that has these boundary values, right? But like I said, it's harmonic on the inside. So what's the function that has these boundary values and is harmonic on the inside? Well, it's just whatever that function is, right? I mean, you can just say it's the harmonic extension of these boundary values into the interior of the domain, right? So let's just give that a name. Hell, I don't know. So this is the function that satisfies. Its Laplacian is 0 inside the domain. And on the boundary, its values are, let's say, the negative of this thing. So let's say it's log of, let's say it's the same boundary values. So it's minus log of w minus z for w in the boundary, right? And then, of course, you just put these two facts together. And you see that these two things imply that this function g epsilon of z and d, blah, 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 that's just the whole plane Green's function minus this harmonic extension of the boundary values. Okay. So that's how you solve that problem. Nothing to it, right? Okay, now, any questions on that or so far? Nothing? Everyone's bored? All right, so that's how you solve that problem. You can't explicitly say you can't say so much what this function is. You mean, what does it matter? It's just a harmonic extension, right? That's good enough. Now, this can be useful, though, because this helps you to compute covariance properties of this field, right? This h epsilon. So one thing I didn't mention is that, so I said this h epsilon, it's an actual function, right? It's a function of z. And it's still going to be, it's still a Gaussian function, right? I mean, that's clear because every element, every one of these things is an actual Gaussian random variable. So this is a Gaussian function, right? So it's enough for a Gaussian function to understand its mean and its covariance structure. So you ask, okay, what's the mean of this thing? Well, it's also going to be mean 0 because h was mean 0, and circle averaging doesn't change that, right? So you have, for example, that the expected value of h epsilon of z is 0. And now we just want to understand what's the covariance of this thing. What's the covariance things? So, in fact, we're going to do the covariance for all possible different combinations. Well, most different combinations of epsilon and z. Okay? So we'll take h epsilon of z1 and h epsilon 2 of z2. And we're going to work out quickly what these covariances are. So in fact, we're not going to do it for all possible cases, but for the two cases which are most important. For all, the different combinations of epsilon 1 and z1 and epsilon 2 and z2. Okay? So the different, what are they? So what is this? So the first case we'll do is, here's our domain D. Here's Z1. Here's Z2. And epsilon 1 and epsilon 2 are disjoint balls around those two. Okay? So that's case 1. And it's an easy exercise in this case. Well, maybe we'll do it really quickly. Maybe I'll just say it and I won't actually compute it. Well, maybe, I don't know. If you ask, what's the covariance of these two? You get lucky, kind of, and it turns out to be just exactly the regular old Green's function. Okay? So this is the original Green's function g for this domain, but evaluated at z1 and z2. So that's why this circle averaging is nice, because when you have distinct points z1 and z2, and then you circle average this thing, and when you have really, really small balls around z1 and z2, the Gaussian field you're left with is basically the same as the original Gaussian field. Right? So the circle averaging doesn't change the long scale covariances, right? Just somehow the small ones. So let's just quickly see how to do this. Well, how to do it. So, okay, so well, there's a lot of notation here, but let's just do it. So h epsilon 1 z1, you can write that's the Gaussian random variable corresponding to the Dirichlet inner product of this thing with the inverse Laplacian of blah blah blah, that uniform probability measure, right? So that's by definition. That's by definition of what h epsilon 1 z1, h epsilon 2 z2 are. And then from the fact that this is a Gaussian Hilbert space, the covariance is just the Dirichlet inner product of these two things, right? These two arguments. So this is just negative Laplacian inverse of mu z1 epsilon 1, negative Laplacian inverse of mu z2 epsilon 2 in the Dirichlet inner product. But now I don't like all these Laplacian inverses, but I can kill one off by using integration by parts, right? So I can put a Laplacian onto one of these guys. Let's put it onto the first guy. Why not? Okay. And then I have negative Laplacian inverse. Well, same thing in L2. Okay. But I don't know. Let me, instead of writing negative Laplacian inverse of this z2 epsilon 2, let me use this d notation, this gd epsilon 2 z2. Okay, Nicola? Yeah. 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 Oh. So you're worried that when you take Laplacian inverse and then reapply Laplacian that you might not get back the same thing, or? That's a good point. That's a good question. I mean, I think in this whole thing, you're mostly working in just a distributional sense. So, I mean, you can get away with anything, I think. Is in the Hilbert space. Yeah, no, definitely. No, that's true. I mean, that I've always just, Yeah.
then you're going to do, I mean, it's harmonic away from the epsilon.
Yep, yep.
So it's 0. It's harmonic inside it, so it's 0.
Yep.
You have this kink
Yep.
somewhere, on the boundary.
Yep. But the kink is the problem, right? I mean,
So the kink is the problem, but just by the geometry of it, you can see that it's going to give you a
uniform probability measure.
It gives you a uniform value there.
No, I agree. I mean, so, my usual answer is just, I mean, so really, okay, so as long as it's true in this part, right, on the whole plane, you're fine. Because in the domain itself, all you're doing is subtracting off a nice smooth function, right? This h epsilon zd is going to be as smooth as you want. So there's no problem there. This thing will be, completely differentiable, everything. The real problem is with this guy, with the whole plane Green's function. So you have to ask yourself, yeah, what kind of function is that? And it's easiest probably if you actually just turn it into a radial problem. I'd like to turn it just into radial coordinates instead. And if you look at it, if you just draw, so if you put, if you graph this function just in terms of the radius, right, the distance in terms of the distance w from z, well, it just looks like this, right? It's small, or it's a really big value. It's like minus log epsilon. And then you have this little kink, which kicks in, right? And you start decaying logarithmically towards infinity. And you have to check. So you have this kink. You're exactly right. That's the problem. And why that kink is actually in the Hilbert space, I don't quite know. I don't quite know, honestly. That's edges of the boundary. Yeah. But how do you deal with the kink, though? That's the. No, it's a completion. I agree. And everything you want is going to be in right. Everything you want is going to be. I mean. No, I know. I totally believe it. But if you were to ask me to provide which you kind of are, asking me to provide a fully detailed proof of that, I wouldn't know totally what to do. But you mean, yeah. Yeah, that too. That too. It's too rough? Yeah. No, I think, Nicola, he raises a very valid point, I think. There is something probably you should check here, but in this particular case, it's so nice that I can't believe anything would happen. And to answer your question of what you have to do to exactly check, ask a functional analyst. So sorry. Right. What was I doing? Right. So how do you compute this? Let me think. We're trying to compute the covariance in this case, right? So by definition, the h epsilon 1 z1 is this. It's these two random variables, right? Just integrating against the inverse Laplacian of these measures. Then that's just the Dirichlet inner product of those two inverse Laplacians, right? Then you use integration by parts to pull one of those Laplacians off, right? Now you're in the L2 inner product of this measure, since I used to pull off the Laplacian, against this thing, this inverse Laplacian, which I'm just going to write g d z2 epsilon 2. Okay. Right. But now what are you doing? So what is this L2 inner product? Well, you're just integrating this function over this measure, right? But this is uniform probability measure on the disk of radius epsilon 1 centered at z1, right? So you're taking this function gd of the potential corresponding to the mass on the unit charge on this circle, and you're taking that potential and you're integrating it over this circle here. Now, what do you know about the potential on this circle? Way over here, it's actually harmonic, right? So when you take a harmonic function and you integrate it over this circle, what do you get? Just the value at the center, right? Or you average it over the circle, I should say. You just get the value of this at the center, right? So this just works out to be GD of Z2 epsilon 2 evaluated at Z1. Okay? Clear? And now, what's happening? That was supposed to be G of Z1, Z2, right? Oh, yeah, and why is that? That's right. Why is that? Took me a minute. So why are these two things equal? Why is the, so this one, in this case, what's the difference? In this case here, you have a uniform charge distribution on the circle, right? And you're evaluating what's the potential at the point Z1. In the other case, well, the Green's function, the way to physically interpret that is you have just a point mass of charge at Z2, and you're evaluating what's the potential at Z1. Right? Why are those two things the same? And that's exactly like Gauss's theorem or whatever, again, right? It says that you can, it doesn't matter where the charge is distributed as long as it's on a circle, right? The circle can be of any radius you want. And as long as it stays within the domain. Is that clear? That's just physical reasoning for why those two things are true. There must be some other quicker way to see it, math way to see it too, but that's the easiest way to see it, I think. Yeah. So that's case one. That's the nice thing. The long-term correlations aren't changed, aren't affected. Now, okay, we'll get rid of this. So case two, really quickly, is when you have just, here's your domain D again, and now you have just one point, say Z, and two concentric circles, epsilon 1 and so radius epsilon 1 and radius epsilon 2. Okay? So what's the covariance in this case? Well, let me just skip right to the end. You can use the exact same trick, right? So in the very last line, what you're going to end up with, if you skip to the very line on the bottom right, just changing the notation, you're going to end up with L2 inner product of uniform measure on the circle of radius, let me think here, epsilon 1 centered at Z1, integrated against the Green's function centered at Z2 with radius epsilon 2. Okay. So what's the value of this thing now? So you're taking the Green's function. Let me think here. How are you doing this? You're taking, this means the Green's function corresponding to unit mass at Z2, or no, unit mass on the circle of radius epsilon 2, centered at Z2. Right? So you have unit mass there, and then you're asking what's the potential, what's the average value of the potential on the bigger circle, right? Okay, now clearly I did this wrong because it would have been easier to do it the other way, right? Well, so in this case, say if I'd done it the other way, say I put the mass charge on the unit mass, center it on the big circle, right? And then I ask, what's the average value of the potential on the smaller circle? Well, inside the big circle, the potential was constant, right? So the average value is just that constant. Right? Is that clear? So it's much easier to do it that way. So let me just switch a little notation here. So let's put, just to match my picture. Okay. So again, just on the small circle, we're averaging the potential created by a unit mass charge on the big circle. So what is the potential on the, what's the potential you get by putting the mass charge on the big circle? Well, inside you get minus log of epsilon 1. Okay? If you take minus log of epsilon 1, average it on this circle, you're going to get minus log of epsilon 1. Careful. No, I lied there. I lied there, right? I lied. Why did I lie? Okay. I ignored the boundary conditions is what I did. Right? So let's try this again. You get the value of this Green's function at the center of the circle. Right? Let's do that. So you're going to get GD of, well, there is no Z1. This is all just Z.
Which one is larger?
Epsilon 1, I guess. Okay? So you get GD Z epsilon 1 of Z. Right? I hope that's right. Any questions there, or did I do it right? Again, it's just you're averaging this constant function, or okay, you're averaging, oh God. No, that's right. I mean, I just got to think about why. Is it clear why that's right? Yeah? No, because the problem was that that's only if it's full plane. I was using the full plane condition. I was forgetting about the zero boundary conditions. Okay? That's the problem. So, and that's actually important because that's the next thing we'll have to do really quickly is work out what the contribution is from this term here. Okay? So in fact, let me write this down really quick. This is going to be, so it's the minus log epsilon 1, okay? But then minus h of, how did I write that? Epsilon 1 z at z corresponding to d. Okay? Is that clear? So again, it's just averaging a function, a harmonic function over some circle. That's how you get the value at the center, and this is just the value at the center. Right? Now, you could just leave this thing as is. Right? You could just leave this quantity as is, but it's actually nice if you compute it, if you actually compute what it is. And it turns out to have a nice expression. And since someone asked me exactly what it is last night, now I know how to do it, and so I'll do it now. Okay, so, it's not super important, but I'm sure Scott will say this. You'll hear him say conformal radius a few times probably in the next couple days, so we might as well know what the conformal radius is and how it relates to this quantity. Okay, so let me just take a brief diversion here into conformal radius. Okay. So again, here's your domain D, and you have some point Z inside. And the conformal radius is just a way of saying, how much of a circle does D look like when viewed from Z? Okay. So how you do it is you map this thing into a circle. Now the unit circle, so this is, that's radius 1. And you send Z to 0. Okay? So you send Z to 0. There is a conformal map that does that. In fact, this conformal map, there's a whole family. You can still take this thing and rotate the circle if you want, right? Once you're done. Right? So you find the conformal map that does that, and then the conformal radius, that's just defined to be, you take phi prime of z, so the derivative at that point, look at its modulus to the negative 1 power. Okay? So that's just by definition. That's the definition of the conformal radius. Okay? And the claim is that, let me see, what's the claim about this thing, about this, when you take this this function it's the log of the distance from your selected point on the boundary, and you harmonically interpolate it inside, harmonically extend it inside. The claim is that if you take h epsilon z, the harmonic extension of this function, actually evaluate it at the point z, then what you end up with is you get the log of the conformal radius. All right. And maybe the minus log, I'm not sure. We'll see in a minute. Okay. So why do you get that? Well, let's look at what I just erased, which is that, remember what h solves. So h solves the Dirichlet problem. It solves the Dirichlet problem where you have the boundary data is log of distance from the selected point. And of course that's just the boundary data. And then inside your harmonic. Yeah. Okay. So that's what h solves. We're just trying to evaluate it at this single point now, right? So the nicest thing to do is, in fact, transform the problem. Instead of trying to solve on this domain, D, use your conformal map to solve it on the circle instead. Okay, let's do that. Okay. You want to fix that for me? Oh, sorry. Thank you. Thank you. No candies? You're out of candies? Oh yeah, I wouldn't mind actually. Fuck. Thank you. Raspberry too. Okay, so right. So transform this problem onto the circle instead. Right? So now we have, let's see, we want to look at the function. What function do we want to look at? I'm always going to get this wrong. Let's say G is so G of, need some notation. G of Z prime is H evaluated at phi inverse. That's right. So it's this H function. So if I did this right, this should be a function from the unit disk into R, right? So it's the function from the unit disk into R, and it satisfies. So you immediately know that its Laplacian is going to be 0, just by conformal invariance of the Dirichlet problem, right? So that's true for Z prime in the disk. And what's the boundary data? Well, it's just that it's the push forward or the pull back, whatever, of the boundary data over there, right? So it's going to be minus log of, let's see, phi inverse Z prime, well, minus Z, Okay. Sorry if that's a bit confusing, the phi inverse z prime minus z, but hopefully we can follow. So that's that. And we're interested in what, remember over here, we're trying to figure out, the goal is to figure out what is h epsilon z d of z. We only want to evaluate this function at this one point. That's it. Okay. But when we transform to this problem over here, well, we sent this point z, we sent it to 0. Right? So conformal invariant of Dirichlet problem again, all we're trying to do is find what's g of 0 for this thing here. But now we just have a harmonic function. We want the value at the center. So we just integrate the boundary values, right? So you get g of 0 is 1 over 2 pi integral over z prime equals 1 of the boundary values, which are log of phi of z prime, no, phi inverse z prime minus z. Okay. So there's the expression, Dimitro. What the hell is truncated log? Oh, no, no, not here. This is just log. It's just. Oh, yeah, sorry, that's right. This actually doesn't depend on epsilon. No. Yeah, this doesn't depend on epsilon, sorry. Yeah, this is kind of dumb notation. You're right. Yeah, no. Remember, the original thing was it was just the. This was just this this function was supposed to be the harmonic extension of this boundary data into the interior. There's no epsilon dependence there, so I have no idea why I'm writing that actually, but why not? So we want this thing, okay? Now here's okay. Here's a quick way to evaluate this integral. I'm not entirely sure it's kosher, but we'll do it anyways. And so what's the trick? What's the trick? So again, it's over z prime, right? Z is constant here. Don't forget that. Z is constant. So the trick is, let me think. So you're integrating a harmonic function, right, over the circle. It's a lot nicer if you can integrate analytic functions over the circle, right? Then you just get the value at the center by Cauchy formula, right? So let's just add a little trick. Since z prime is 1, let's take this thing and divide by, and this is also, I should also write, I'm going to, one more thing, z is phi inverse of 0, right? That's the other thing you can do. Right? So that's phi inverse of 0. Now divide this by z prime, sorry, which is fine because z prime has modulus 1. Right? So the log doesn't care about that. Now recognize that if I get rid of the bars, I can get rid of the bars if I just take the real part of this thing. Right? No problem there. Now what kind of function do you have here as a function of z? Or z prime, sorry, a function of z prime. It's analytic, right? And it's perfectly analytic everywhere, except for maybe when z prime is 0. Right? But when z prime is 0, well, it's basically the derivative, right? So what you do is you take this function, you replace it at 0, you replace it with the value of the derivative at 0, right? So it's phi inverse prime of 0. So you take an analytic function, evaluate it over the circle, you just get the value at the center, which is log of phi inverse prime of 0. Right? This whole thing. And then you take the real part of that. And of course, that's the same as just doing, well, And then you just use, well, use inverse function theorem or whatever to check that this is the same as log of phi prime of z. Okay? Now, as I look at that, I see that there's a couple things that might not be quite right. Shouldn't there be there's an I here, right? When you do Cauchy, is that right? When you do Cauchy, what's this called even? Is it? Okay. Yeah, I guess you're right. No, I guess you're right. It's just the mean value property of a, no, I guess you're right. And you just put these bars on there, right? And once you add this z prime, then it's a harmonic function or something, right? Yeah, no, that's true. That's true. But the only thing I'm worried about was how you there's the problem of the singularity at zero, right? But I think that smoothed it out somehow. So I think Ron's right, actually. It's just yeah, it's removable, exactly. So it says that this function is analytic, therefore its real part is just harmonic, right? And then you just use mean value property, like Ron said. That's right. And apparently someone told me that this goes by the name of Jensen's formula. So if you don't believe me, which you probably totally shouldn't, this is Jensen's formula. Okay. All right, so that took a really long time. But the point is, so there is these two cases of the covariance for this H epsilon field. When the two balls are separated by some distance, right? And when they're just overlapping like this. And those are the only two cases you worry about. There's also the case, of course, where you have two balls and then the disks intersect somewhere, right? But, nah, you just don't worry about that because, when epsilon gets small, right, you only care about epsilon small in this case. And epsilon small enough, those two disks won't overlap anymore, right? So you just don't worry about the covariance in that case. So, okay, so let's go back here really quick. So the answer here for what was the covariance in this case, it's just the log of the bigger ball, minus log of the bigger ball, minus this constant here, which actually doesn't depend on epsilon, like I said, even though notation looks like it. And this constant is just the log of the conformal radius. And, yeah. So it's minus log of the conformal radius. And that might actually be plus. I'm not sure. I could be off here. No? Let's just say it's minus for now. Yeah, so this is just put plus minus there. I'm not totally sure what the sign is there. I probably screwed up so many different ways by this point. Okay, so the quick observation you make out of that is that if you take this H epsilon of, so if you fix z, and you let epsilon vary, then what's the variance of this thing? Well, it's minus log of epsilon, right? And then minus this fixed constant log of the conformal radius. Or if you call this thing, if you call epsilon, say, call that e to the minus t instead. Okay, so we'll call that e to the minus t. Then minus log of e to the minus t is just t. Okay. And so this process here is a function of t. Think of this as a process in t now. So as a process in t, it's Gaussian. It has variance t, minus some stupid little constant, but we'll forget about for now. So it's Gaussian, it has variance t, and so you think, okay, it's Brownian motion. Right? And in fact, that's what it turns out to be. The other thing you really should check is you should check the covariance structure. You should say if you take, say, h of e to the minus t z, and h of e to the minus s of z, then what is the covariance of these two things, at least for the two different epsilons? Right? But that comes from exactly this formula here. It's going to be minus log of the bigger radius, right? Plus this log of the conformal radius thing. So it's minus log of, let's see, the bigger radius. So you get the bigger radius when you put in the whichever is smaller, s or t. Right? So it's minus log of, well, you're going to get t, but you're going to get the smaller of these two things. So it's actually going to be s min t. Yeah, let's just write it. And then minus the log of the conformal radius again. Okay. So now you have a Gaussian process where the covariance structure is given by just the minimum of s and t. Okay. And so that tells you basically that this Gaussian process is a Brownian motion. Okay, so this is for fixed z again, right? So you have t goes to h e to the minus t of z is a Brownian motion. So that's that part. Now what? Okay, so my plan was, there's only about 10 minutes left. So my plan was to talk a little bit about how you construct this, these, or the construction of these measures, these e to the gamma h type measures, and then how these things are, sort of, they're only measures, but you you think of them kind of as random metrics, or even as random surfaces if you want. I was going to talk about that, but I mean, is there any, really burning questions anyone has before time runs out? On anything, or about maybe like the stuff Scott talked about this morning, or no? No one's just dying to know right now? Okay, well, let me just briefly mention how you use these things to build. Ivan, yeah. Other approach to. Yeah. Right. Can you do similar things, you mean? To make which, sorry? Oh, to talk about the discrete Gaussian free field? Not in 10 minutes, sorry. I mean, really, these issues, I'm not sure they actually carry over to the discrete side anyways. I mean, they kind of, you can talk about the Green's function on your discrete graph and make similar computations, but this really uses the fact that you're in 2 dimensions, right? Because all these computations are based on the Green's function. And this is... No, that's right. I mean, there the Gaussian free field is a function, of course, on a grid, right? So you don't have these issues at all. Okay, so let me just really quickly say how you build a measure out of these things. So you want to construct a measure from this Gaussian free field. The problem, of course, you can't just do that right off the start, is because well, it's not the Gaussian free field isn't a function in any sense, right? It's only some sort of distribution. So how do you construct a measure out of that? Well, the trick is you do this regularization procedure first. Then you get yourself a function. Use that function to build you a measure which is absolutely continuous with respect to Lebesgue. In fact, an entire sequence of measures indexed by this time parameter. And then you let time go to infinity, and you end up with a limiting measure, right? So what you do here is you just observe that because this h of e to the minus t is a Brownian motion, that means that the exponential of, say, gamma times h of e to the minus t of z minus minus gamma squared over 2 times t, that means that this thing is a martingale. No, log t, right? Oh, damn it, I'm in the wrong time. Question is it t? Yeah, no, it's t. It's t. It's fine, right? It's t. Right, this is the standard fact that if you have a Brownian motion, then e to the gamma bt minus gamma squared over 2 times t, this is a martingale. Okay? That's just a standard fact. If you don't know that one, well, check. Okay? So now you take this thing for each z now, this is a martingale. Okay? For each fixed z, you can say that's a martingale. And now you just multiply this thing by Lebesgue measure. So think of that, that's a random measure. This is a measure on your domain D. That's the radon-Nikodym derivative. Okay? So you have a random measure now. And now in the sense of measures, you take a limit of this thing as t goes to infinity in this case, I guess. Okay? So you take t goes to infinity, and you get a random measure e to the gamma h. Okay. Why you have to take gamma less than 2? Okay, good point. So right, so this only works for this only works if gamma is less than 2. That's an important thing. So why does it only work? Well, you can guess probably. I mean, I'm going to give you the short answer. Because so it's a martingale, right? So its mean is okay. So what's going to happen for this martingale? This is a good point. So for a fixed point z, what happens to this martingale as t goes to infinity? Just for a fixed point z, what happens to that quantity there? So it's a fact about this this exponential martingale. Hopefully you know that as t goes to infinity, this thing goes to 0. In fact, almost surely. So this thing will go to 0 almost surely. Okay. So for each that will happen almost surely as t goes to infinity. So no, it's just because this is a Brownian motion with negative drift, right? So it goes to infinity, negative infinity, sorry. That goes to negative infinity, and so e to it goes to 0, right? Right, so that's why. So for each fixed z, you're going to see that this density goes to 0. Right? So then you ask, how do you actually end up with a measure? Right? How is it that you get this measure you get here? How is it going to be interesting at all? Right? So that tells you, for one, that the measure you get, you're not going to have a density with respect to Lebesgue. Right? You're not going to have some sort of density with respect to Lebesgue measure. The density, this e to the h measure, is going to be completely singular with respect to the Lebesgue measure. In fact, what will happen, so what actually happens is, so for each fixed z, this goes to 0, but you have uncountably many z that this thing, you have uncountably many versions of this, right? You have one of them for each z. So what you expect and what actually happens is that some of them manage to be exceptional, right? Some of the z's manage to be exceptional, and this thing doesn't go to 0 for those z's. And somehow what happens is the things for which this thing, if it doesn't go to 0, this thing actually has to blow up. You'll see that this martingale will blow up. I mean, one way to see that too is if you look at this exponential martingale, It goes to 0 almost surely, but for every finite time t, its mean is 1. Right? So this thing has mean 1. Right? So if you ask me, if it goes to 0 almost surely, most of the time it's really small, right? How does it have mean 1? Well, it's because in a few rare events, it happens to get really, really big. Right? For an event of small probability, this happens to get really, really big. Right? Now, for a fixed Brownian motion, if that event of small probability, as t gets big, it just kind of disappears. Right? But here, what happens is you have so many different Brownian motions that there's enough of those events of small probability get together and make this thing happen. They make this thing actually converge. Okay? So it's sort of a large deviations type thing. You have so many of these things that get big that in fact you can make this measure actually converge to something non-zero. But again, this only works in the gamma bit less than 2 case. Right? And why is gamma less than 2? I mean, so why is there this trade-off? I mean, why when you increase gamma, somehow do you get a smaller and smaller measure? And that's not quite make sense. But see, when gamma gets too big, you saw this in Bertrand Duplantiers' movies, right? You saw when he had these movies where the e to the gamma h, as gamma gets bigger, you just get these more and more spikes, right? And the spikes, what they correspond to is they're just the fewer and fewer points z that survive. Right? Because as gamma gets bigger, well, the drift gets bigger here, right? You have this negative downwards drift on your Brownian motion. And as the drift gets bigger, in order for this thing to survive, in order for this e to the gamma bt minus, to stay important, the Brownian motion has to be more and more exceptional, right? It has to do more and more weird things. It has to be weirder and weirder somehow. No, there is a computation. There is a computation. And if you check it in Duplantier Sheffield, you actually see it. Now, off the top of my head, I can't quite do it. I don't really know it. But in fact, you even see it quite sharply in their proof that gamma equals 2 really is critical. And I should mention, there's also similar models like this. There's these models called multiplicative cascades, which are very close to this type of thing. It's actually sort of if you want, you can think of it as a toy model for this type of thing where you have random measures that only survive because of, they only survive in the limit because of some exceptional set of points where, the Brownian motion or whatever does something really amazing. And in the same, you'll see the same case once you have a sort of gamma parameter, and when gamma gets too big, the measure no longer survives. Okay. Now Nicola's question is right, is why is gamma equals 2? Why is that actually the critical value in this case? And, well, it's just a computation, more or less. I mean, Scott did this, he did this, I guess, yesterday, I think, on the board. How do you actually check that when you have this type of random measure, that the limiting measure is not 0? Right? And this is, it's the basic example here. It's basically, this measure is sort of you can think of it as like a martingale measure. So that means this is a positive martingale. So it's going to have a limit almost surely. Okay? But the limit might be 0. That's the problem. Right? And when gamma is bigger than 2, that's exactly what happens, is the limit is 0, more or less, for all your z's. Okay? And so there's no chance that this measure survives and gives you, it becomes 0 is all it does. So it's a boring measure to study. And yeah, Ivan? You think that's a good enough question? Are you going to fix my sandal too? No. Yes. Okay. So, it's 4:30. I don't know. Yeah. I don't really think I have anything much more intelligent to say, actually. Any questions? Any burning questions? I didn't address the stuff about the stuff he talked about this morning about these two distributions being the same. These two random distributions having the same distribution. Yeah. Why do they converge? Okay, that's another computation. It's a computation. You need to so it's like when you have a positive martingale. Why does a positive martingale converge? what type of thing do you need for that? So you always need some sort of uniform integrability, right? That's the bare minimum you need to get by, is some sort of uniform integrability of your family of measures. So, I mean, I can tell you that sort of the cheap computation is, yeah. Sorry? No, this one by itself. For a fixed z, it's not. When you integrate, though, then some stuff happens, right? So what you do is, when you say measure, the easiest thing to do is, you shouldn't think about this for a fixed z, because if you do this for a fixed z, nothing nice will happen, like Nicolas is saying. This martingale itself is not uniformly integrable for z, for a fixed z. But when you say a measure converges, one nice way to check that is just take this radon-Nikodym derivative. Let me think. Minus gamma squared over 2t d2z. This is two-dimensional Lebesgue measure, right? Take that thing and integrate it over some set A. Okay? So now you just have a random number, right? It's just a number. And basically you can check that, or you think about it as a number, but it's a process in t. And as t varies, this number varies. And you can sort of check, you can convince yourself that because the integrand is a martingale, is a positive martingale, then the whole thing is a positive martingale, right? Basically, when you add up a bunch of positive martingales, you're going to get a positive martingale again. So now you want to take a limit of this as t goes to infinity, and you want to see, I mean, you know the limit exists, right, because it's a positive martingale. The only question is the limit 0 or not? Okay? So, well, you need uniform integrability of this thing. So to answer your question, here's one cheap way you can do it. An easy way to get uniform integrability is if you have a martingale, say mt, you want to know if it's uniformly integrable. Well, if the existence of higher powers is enough, right? So for one, just square this thing and take the expected value. And then if you take the supremum of this over t, if this is finite, then you're in business. Then you'll know that this thing has a limit. Okay? That's one cheap thing. This is certainly sufficient, but it's by no means necessary. And usually this condition is not sharp. But I'm pretty sure, now don't quote me entirely on this, for this particular martingale, if you take it and you square it, so you take it, you square it. When you square it, squaring is nice for this type of thing, right? Because you get a double integral now. Right? You get a double integral, and then you want to take the expectation. So you pass the expectation through the integral, right? That's no problem. That's Fubini's theorem. Everything's positive, so there's no problem there. You take the expectation, you pass it through. You're going to get some weird function. I don't quite know what you're going to get. You're going to get some weird function of t and z and another point w. So you take that function, you integrate it, and you just check that it's uniformly bounded in t. Ron? Yeah? Yesterday, I think. Yeah. Of this thing, yeah. 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 Really? Even just the expectation? Is that true? Yeah? Really, even for gamma less than 2? Okay, okay. Oh, really? Okay. Just for overlapping circles. Yeah, okay. That definitely could be a problem because... Oh, sorry. So you were saying that when you have overlapping circles, that the expectation of this, like 2 terms there, for example, can still explode even when gamma is less than 2. If you have overlapping circles. Fixed epsilon, I guess, right? Yeah.
Using a calculation like this, you find that it is infinite if gamma is bigger than the
Square root of 2, yeah. Yeah.
If gamma is less than that, you have a second moment,
Yeah.
and you have magnitude b as a second moment argument.
Yeah.
Now, when gamma is between the square root of 2 and 2, you have to use a different trick.
Yeah, exactly.
The second moment argument fails.
Exactly, yeah. Yeah, okay, yeah. No, it's, I mean, I'm not sure if it's what you're saying point-wise is right, but okay, it could be. It could be. I'm not even sure. But that's how I was trying to answer your question back there, is that if you take the expected value of this and then look at like a supremum over t, you'll see this is finite, but only for gamma less than root 2. Okay? Not for the full range of gamma, not right up to gamma equals 2. And this is typically what happens because this type of test is not sharp. It's easy, but it's not sharp. That's the problem, right? So, you know, I mean, you have to use other tricks then. You know, the nicest trick you can do is when you get into this situation, you can start taking, if you can, you start taking lower moments, right? I mean, a sufficient condition for a martingale can diverge is all you need is that mt to the 1 plus epsilon. If that thing is uniformly bounded, then you're good. But taking an integral like this to the 1 plus epsilon, well, not so easy to compute, right? It's going to be a pain. So that's one cheap way of getting that this thing actually converges for gamma less than root 2, just expectation. And then, like Scott says, for gamma between root 2 and 2, you need more tricks. And yeah, I forget what the trick is there. But it is in this Duplantier-Sheffield paper. And it's one single trick that works for the whole range, right? It's not, you don't need a whole bag of tricks for different parts of this range. Just gamma between root 2 and 2. It's, I don't know, I'd have to check. I don't remember exactly how, but, I mean, it's not fun. It's not fun like this one is, but it works. It's fine. Okay, so that's why those measures exist. Ivan, did you have a question? Oh, okay. I thought you did. Okay, I don't know. I have nothing else to say, I don't think, unless anyone have questions about anything. So I didn't cover anywhere near what I thought I would, but if you have questions, just ask, I guess. And then we can, yeah, just find me and we can ask. Anything else? No? Okay, let's go.